name is Grela. I'm the managing director of the Spanish company TRedess, and in the next 15 to 20 minutes, the idea is to try to cover more or less the same concepts that we have been already seeing in the presentation from Phil and Martin, but trying to focus more on the product side and on the manufacturer point of view. Okay, so I will just give a very brief introduction to TRedess as a company and our experience working in SFN networks for DVB-T, T2, or DAB+. Then I will try to cover a little bit what have been the main events or what is the circumstances we are now in that have been raising this topic of synchronization as a higher concern for all of us. And then the focus of the presentation will be what are the new features, functionalities included in the modern synchronization devices or DAB+ transmitters in this case, to try to compensate or to cover or to fight against those new threats, okay? And then to try to come to some conclusions, okay? So, I mean, for whoever does not really know us yet, TRedess is a Spanish company. We design and manufacture DVB-T, T2, TV transmitters with multiple standards, also DAB+, and also 5G broadcast transmitters, okay? We count with a background of around 30,000 TV transmitters deployed in more than 70 countries. And on the DAB side, we nowadays count with around 700 DAB+ transmitters operating in around 15 countries. And I mean, in the next few months, due to the projects we are involved, we very soon will find a figure of 1,000 transmitters deployed, okay? We joined the World DAB just a year ago. So more than happy to be also forming part of these seminars when we are invited to participate. This is a view of, I mean, more focus on the European side, although we have done also many projects in Asia, Africa, and many other parts of the world. But this is more or less a view of where we are present in Europe, where our transmitters are being present. This is more or less showing in the orange logo where we have transmitters. Most of these networks that we have been deploying in the majority of the countries in Europe are based on SFN networks, okay? So based on that background, that is what we are going to be sharing today, okay? So we as a manufacturer, we count with lower power, medium power, or higher power transmitters. And from the synchronization point of view, we may have a built-in GNSS receiver built into the transmitter, or we can have like a standalone kind of GNSS receiver with certain functionalities that generally are improved versus the built-in option, okay? Where we are talking about the multi-constellation, the multi-band concepts that Phil was already touching on, and I will try to dig a little bit more in the next minutes, okay? So why we are, let's say, more why we are really having this topic of the synchronization more in our tables nowadays, okay? I mean, clearly, I mean, we have been all this previous hour talking about SFN, and clearly when a network operator wants to build a network, if they can use SFN, of course, they prefer to use it, mainly because it brings a much more efficient use of the spectrum, a wider coverage area, a reduction in the energy consumption, lower CO2 emissions, and in the end, lower transmission costs, okay? But as Phil was already indicating, also Martin, SFN implies a very strict timing and frequency synchronization. So you need to find the methods of doing that kind of synchronization. Around the world, I mean, and there are different methods and techniques to find this synchronization, but what we have been seeing is that you always need to find a trade-off between what you want to achieve and the costs that you need to raise in order to achieve that, yeah? So the two most commonly used SFN synchronization methods are clearly the GNSS-based one and the PTP systems, okay? Each one has its advantages and disadvantages. Some of them have been already mentioned here, but clearly the main advantages from the GNSS-based kind of system is the high accuracy that the system provides in terms of precise timing, what is ideal for SFN requirements, the total independence on the IP network, so you are not affected by the network traffic or jitter, is simple to deploy from the point of view you just need to have a GNSS antenna and a receiver at the transmitting side, and is clearly the more standardized and widely used system. So products are really mature and interoperable. Disadvantages, as it was being mentioned already, you need to have a good visibility of the satellites. So if you are located in a valley, in a canyon, or you are having a poor antenna installation, then it can cause potential problems on the timing quality and SFN problems somehow. Yeah. It's vulnerable to interferences like the jamming and spoofing that we will be commenting a little bit in the next minutes, and it's not a centralized control system because basically each site is independent, okay? On the other side, PTP brings the advantage of being more a centralized distribution timing system. You don't need to use satellite antennas at the sites, and you are more resistant against GNSS outages because you don't really are affected by jamming or spoofing. You are just based on the PTP infrastructure. But at the same time, this has the disadvantage that you need to have the PTP network, the network ready to operate with PTP. Okay, so the switches and the routers must be able to support that kind of protocol. So it's more sensitive to congestions, and that could be affecting the accuracy on the timing synchronization you need. It could be seen as a more single point of failure because you are basically depending on the grandmaster in the network, although generally I would guess that always there is a redundant system there to protect the network. And from the timing accuracy perspective, I mean, PTP was generally known as, let's say, a lower timing accuracy than GNSS, although recently it seems that there are some projects that are already bringing quite an interesting time accuracy also based on the PTP protocol. Okay, so the reason why the reasons why we are now more concerned about the synchronization, I would divide it in two main things. One thing is events that have been happening in the recent years, and the week number rollover. I think that the date of the 6th of April 2019 is a day that anybody that has been in this industry probably has in its memory because it was something that really made a lot of us to be having lots of headaches. And then the clear increase in the number of detection of malicious attacks into system, yeah, jamming or spoofing. So going into each one of these two categories, the weak number rollover, for whoever does not really know what that was or did not suffer it, basically it comes with the fact that the GPS system is based on a counter of weeks that only has 10 bits. So in the end, it just can count from 0 to 1023. So whenever the rollover happens on that counter, if the GNSS receiver is not designed to handle that rollover, that could create some SFN errors, okay? So this effect happened already twice. First was happening in 1999, and the second that is more fresh in our memories is the 6th of April 2019. This date, I mean, as far as we know from some of our colleagues in the industry, some network operators really suffer some outages due to this problem, and others had not a very easy previous mode to the event because they really not had to run to prepare the system in order to avoid this failure to happen. Okay. The next rollover is expected to happen in 2038, although I would guess that whatever implementation was done to resolve the problem in 2019 is already making the systems ready for being coping with the next rollover. Okay. And then my previous speakers have been also talking about this, but clearly what we have been detecting in our projects is a clear increment in the number of incidents related with attacks to the GNSS systems, okay? Jamming and spoofing are the most typical ones. I mean, the main difference, as Phil, I think that was already mentioned, is that jamming is trying to block or interfere the GNSS signals, And spoofing is a little bit more sophisticated as it's trying to fool the receiver by generating some fake satellite signals that the GNSS receiver can understand as valid ones, okay? So the most, popular one, or the one that happens more often, is the jamming, okay? But sometimes the jamming is not even deliberate. I mean, it can happen just because of any faulty electronic device that is, let's say, next to the site, or any malfunctioning transmitter with harmonics or things like that, as they were mentioning before. Yeah, but one thing or the other can, in the end, cause some kind of SFN synchronization problems, okay? So the focus now on the presentation is, we are in this scenario, that's where we are, okay? So there are new threats and there are some circumstances that we need to face, okay? So what are the functionalities or the features that the products currently have, the modern solutions that can really help to fight against those kind of threats, okay? So here you have a list of ideas, okay, or techniques or features that the modern devices have already that can help to compensate all of that. Okay, so first idea is to include GNSS receivers that can support multi-constellation. Okay, I will go point by point in the next slides on this. Okay, so first idea is to support multi-constellation. Second idea is to come with GNSS receivers that can support multiband. That's also quite important. Come with GNSS receivers that can also detect these jamming and spoofing circumstances, okay? Count with GNSS receivers that can also support what is called the augmentation systems. I will explain them a little bit later on. When talking about GNSS and PTP as alternatives, it's also very interesting to count with synchronization devices that can operate with both, okay? So you can operate either with GNSS or PTP, having the same device on the network. Then bring as much redundancy as possible in the architecture of the synchronization part of the network. They have been talking in the previous presentation about doing monitoring of how the SFN is performing. So why we don't bring some additional improved monitoring capabilities also on the devices itself, from the, let's say, synchronization devices or the transmitters themselves, okay? So that they can take some actions after whatever they are monitoring, improve the holdover performance, as Phil was mentioning, and the use of anti-jamming or anti-spoofing antennas, okay? So if I go, for example, to the multi-constellation part of the topic, if I go back to probably the networks that were built more than a decade ago, they were based on GNSS-based synchronization systems, probably just dependent on GPS or GPS and GLONASS, okay? The more modern products from synchronization, they are already operating with multi-constellation from GPS, Galileo, GLONASS, Beidou, and even others, okay? And this multi-constellation capability brings a higher reliability on the SFN synchronization because of several reasons, okay? Because just by seeing more satellites, you have a better timing stability, because seeing more satellites implies reducing the timing jitter. Also, if you are being able to see more constellations, if any of the constellations is for whatever reason blocked or things like that, you can continue locking to others. That also helps when you are in urban or challenging sites near buildings or near forests or near valleys, because basically there you can have a better view of other constellations if anyone is especially blocked. You can also benefit from the fact of working with several constellations on the robustness against jamming and spoofing, because if somebody is trying to jam or spoof a certain part of the constellations, you can continue working with the others, okay? Or you can disable to operate with a certain constellation. And then able to operate with several constellations also improves the signal diversity, because each constellation uses different frequencies, coding rates. So in the end, this helps from the reduction of the multipath effects and other things. Okay, so multi-constellation characteristics bring somehow a cleaner and more stable timing lock. Then we go into the multiband. Okay, that is a different thing. Okay, multi-constellation is that the receiver is able to operate with different constellations, and multiband is that you are able to log into the different bands that each constellation is transmitting in, okay? So for example, in this diagram, you can see in the different bands in which each constellation is transmitting. So for example, GPS is transmitting in the band L1, L2, and L5, okay? Galileo is transmitting in the E1, E6, and E5, okay? So each constellation is being received in different frequencies, okay? So the fact of having a multiband compatible GNSS receiver, what it brings you is more reliability on the SFN synchronization, mainly because multiband brings also the capability of reducing the number of errors derived from the ionospheric delay. So, okay, so if you have a single band GPS receiver, you cannot really correct the errors, but if you are operating in several bands, like for example in the GPS, you can log to L1 or L2, or L1 and L5, or L1 and L2 and L5. That can really help to eliminate some of these errors that the ionospheric delay is creating, okay? From the other point of view, using multiband GNSS receivers also brings more resilience to the network because also in urban environments, you can really log into different bands, okay? The same as before with a multi-constellation, it improves the availability and reliability because if somebody is jamming, imagine the band L1, you can continue operating the bands L2 and L5, okay? So that's really an important improvement on the resilience of the network, the fact of operating with multi-band GNSS receivers. And then it also brings along a higher timing precision, mainly because, for example, in the band L5, you are using different chip rates or coding rates, a linear signal structure. So in the end, you can get sharper timing measurements, okay? So multiband, multi-constellation are already helping to really improve the reliability of the system. But also, what is interesting is that the synchronization devices are able to discipline the OCXO based on different sources, okay? So if you have one device at your transmitting site that can really operate or generate the synchronization signals to the transmitter based on GNSS receivers with single or redundant capabilities, also with PTP protocol, and also having like an external source of 1 PPS and 10 megahertz, then the synchronization device at the transmitting site can be able to switch from one source to the other in case you are detecting that any of the sources is becoming unreliable, okay? So here you have a picture of, for example, what is our TRedess MGNSS receiver, where you can have the possibility to work with the PTP protocol, also with single or redundant GNSS receivers, and also to have the external 1 PPS input as an option there, okay? So on the web interface of the device, you can see that the OCXO. So this is showing the two GNSS receivers that you can optionally have in the unit. Each of the receivers has its own OCXO, and this OCXO can be disciplined by either the PTP protocol, the GNSS receiver, or the external 1 PPS source that you can have there, okay? Another, let's say, feature that the modern receivers include is the fact of being able to operate also with the augmentation system. So SBAS stands from satellite-based augmentation systems, and the idea behind this is that the ionosphere is causing the signal diffraction on the NSX signals. This is a fact that you can never avoid, okay? So the SBAS systems, what allow you is that the receivers are not just relying on the signals that they are receiving from the satellites, from GPS, GLONASS, or Galileo, or Beidou, but also they are receiving some correcting signals from geostationary satellites that are is the base of these augmentation systems. Okay, that helps so somehow to improve the position accuracy mainly. Okay, on the GNSS signals. Okay. Then, in the same way as we have been always trying to protect the transmission sites with 1+1 and +1 dual drive configurations, all these recent events are also leading to try to protect as much as we can the synchronization part of the network. And then the latest architectures, apart from the features that we have been discussing so far, bring also the capability to have like single or redundant GNSS receivers, single redundant power supplies, hot swap modules, easy operations, seamless switching between the different sources. So all this is something that is requiring any modern solution that you may need at your network. Okay? And then so far we have been talking about monitoring, but in the previous presentation, they were focusing more about how you externally detect that something is going wrong from the synchronization point of view, okay? And I would like also to bring these ideas, but inside the transmitters and inside the synchronization devices, okay? So if you are able to have devices that can raise already to you an awareness that something is going wrong, then you can react, or the transmitters can automatically react to those kind of scenarios, okay? So the modern transmitters or modern GNSS receivers, what they can just bring you is the capability of detecting that you are being jammed or you are being suffering an spoofing attack, okay? Other mechanisms that you can implement in your own transmitter, that at least we have in our TRedess transmitters, is to detect some inconsistencies between the date and time that you are receiving versus whatever you are expecting it to be, okay? Other way of detecting it is inconsistencies between the geolocalization you are receiving now and the one that you know that you are in because you know where you have been installed, okay? And also you can detect some internal anomalies between the PPS that you are generating and also the source that you are receiving, okay? So if you put together these internal monitoring tools inside of the transmitter or inside of the GNSS receiver that you are using from at the site, in the end, that can help you to conclude that something is going wrong in the current source of synchronization that you are using, and then you can react to that, okay? Either by switching to other valid source of synchronization, and if you are having a device that can also operate with GNSS and PTP, you can switch to either other constellation, switch to another GNSS receiver, or to switch to the PTP mode, okay? So that's an interesting thing that you can automatically switch whenever you are automatically detecting that something is going wrong. Then you can also go into holdover state if you decide to do so, or you can mute the transmitter if that is basically what the best reaction to protect what Martin was saying, that one transmitter failing was affecting too much more people being affected by an SFN disruption, okay? So this is just a way of showing how the internal monitoring tool works in our way, in our transmitter. So basically you have a way of having like a short and long-term monitoring of all the internal parameters. And apart from MERs, efficiencies, and all voltages and currents, you can also get a view of the synchronization signals status and health, how the offset of the PPS is going, the adjustment of the voltages of the OCXO, how many satellites are you seeing? Okay, so based on all this kind of information, you can react to whatever determinate particular circumstances, and these tools can really help you to either troubleshoot potential problems that you can find or to get some proactive health checks for the future, okay? So in the market, there are already several solutions that can cover some of the functionalities I have been talking about. Some of them are covering all of them, some are partially some of them. This one that I'm just showing here is one example that is, let's say, our MGNSS receiver, where you have the redundant architectures I was just mentioning before, with redundant power supply, redundant GNSS receivers, with the capability of having the different sources from PTP to external one PPS, one or two GNSS receivers, and very importantly, capability to operate with multi-constellation, capability to operate with multi-band, capability to detect the jamming and spoofing, and also with the capability to operate, as I said before, with seamless switching between the different outputs, okay? So just to finalize, just a couple of notes that by talking and acting in many of our projects for DAB, and all whatever I have been saying could be applicable for DAB Plus or DVB-T or T2 or any kind of terrestrial transmission. But this is an interesting point that I would like to highlight because probably on DAB networks so far, The use of on-channel repeaters is not so extended, although there are some projects that we have been already delivering on-channel SFN repeaters. But there is a kind of misconception sometimes that the on-channel repeaters also need to have like a synchronization element at the side, and that's not correct. Okay, it's just to clarify this point. That's the beauty of the on-channel repeater, that in the end, to repeat the DAB signal, you just need to have a receiving antenna, your device, and a transmitting antenna. You don't need to have any kind of synchronization system there, because the time that it takes to process the signal is really short, so you don't need any kind of synchronization there. So you are avoiding to bring the signal into the site to have any kind of GNSS antenna, GNSS receiver, and so on. Okay. And another, let's say, final idea is that when we are thinking or when we are talking to some of our customers, they are quite interested about the idea of the multi-band, multi-constellation on the GNSS receiver, and in some of the areas where we have been detecting some of these major attacks, and they are always close to conflict areas, on the countries close to Russia or next to Israel and things like that. That's where the majority of the things have been detected. It's good to replace the existing, let's say, older GPS receivers by multi-constellation, multi-band and anti-jamming kind of features there, but we cannot forget that the antenna needs to be according to that as well. Okay, so it doesn't matter if you put a very high performance GNSS synchronization device on the network if the antenna is not being able to also receive multi-band, multi-constellations, and so on. Okay, so both things need to be aligned somehow. And also the fact of using anti-jamming antennas helps to prevent some kind of interferences from let's say the jamming or spoofing people. So as main conclusions, clearly nowadays the AV networks are considered strategical and critical communications for most countries. Whoever can operate SFNs, they will do it because of the benefits it brings. The current geopolitical situation and recent events have really raised the concern about synchronization. So there is a clear increment in the number of attacks that we are detecting in the field, but we still need to keep hopeful about that, because somehow there are existing solutions already into the market that are helping to counterpart that, or to prevent those attacks to really affect in a deeper way our networks. And among that, especially the use of multi-band solutions, multi-constellations, receivers that can detect the jamming and spoofing, using antennas that can also help to prevent those attacks to be happening, using devices that can really cope with PTP and GPS or GNSS systems at the same time. And these monitoring solutions, also external, but also internal on the devices, can really help to detect that something is going wrong already and react to that by either muting or switching to other source or things like that. Okay, so and that was more or less the idea of covering from the product point of view, what is available nowadays to try to fight against these new threats that we have in front of us. Okay.